All right, ladies and gentlemen, let's get started. One of the things that we get really excited about at the Edge AI and Vision Alliance, and I personally get excited about, is the idea of ubiquitous, always-on AI, right? AI that just becomes almost kind of invisible. It's just, in the background taking care of you. And we see that a little bit now with, speakers that have wake words, things like that. To do that, you've got to be doing AI processing, and you've got to be doing it continuously. And what that means in turn is you've got to be able to do powerful AI at extremely low power, right? Because a lot of these devices are going to be battery powered. And what's cool about this talk is that's exactly what this is about. So designing the next ultra low power, always on solution. And our speaker is Amol Borkar. He is Director of Product Management at Cadence, specifically for the Tensilica Vision and AI DSPs. He's got a long record of managing successful product launches, and has a PhD in signal processing from Georgia Tech, correct? So Amol, thank you.
Yeah.
Last you checked, excellent. All right, thank you very much and welcome.
Thank you. So my name is Amol Borkar. I'm the Director of Product Management and Marketing for the Vision and AI DSPs at Cadence Tensilica. And for today, I'm going to go over designing this next ultra low power, always on system. So let me get a few things about our company out of the way. So if you're not familiar with Cadence and Tensilica, we're a very successful IP provider. So we have shipped over 40 billion processor IP. In terms of DSP licensing revenue, we are number one. 19 of the top 20 semiconductor vendors use Tensilica IP in one or more of their products. And we have a very strong partner ecosystem, over 200 partners and growing. Aside from the business, want to also highlight a few places where we've had some recent success. So one example is Unisoc, formerly Spreadtrum, multiple application processors featuring our Vision DSPs in there. Then we recently made an announcement with Light Semiconductors where they had instantiated several instances of our Vision DSPs to do accelerations for their depth perception stack. And last, we also had a successful engagement with XVisio, one of the leaders of SLAM and 3D camera tracking. And we have a demo for that at our booth right outside. So now that we got this stuff out of the way, let's go into the meat of the talk. So basically here I'm highlighting the trends in processing and the different types of sensors that I use. So if you look at the top row, you've got automotive applications, robotics, drones, mobile phones, and a variety of different sensors are used over here. You've got image sensors, radar, LiDAR, 3D ToF sensors, the large number of sensors, high FPS, low FPS, sensor fusion, all sorts of things going on. But one place that has been picking up a lot of activity is this. Ultra low power AI and this always on island. So let's dig a little deeper into what exactly this is. So always on basically is methods or methodologies or protocols of how you want to wake up a device. Now, many of these of us are very familiar with these, and some examples are using HDMI, GPIO, gyroscope type of things as input sources to wake up your device. And recently, we have been seeing an uptake, obviously, with using microphones and ultrasonic sensors. This has primarily been due to the proliferation of TinyML and these TFLM type of networks. Now, while audio-based wake-up solutions have been around for a while, one place that has been picking up also a lot of activity is using cameras for the equivalent of the audio part, being visual wake words, doing things like human presence detection, people detection, hand gestures. And there are many ways we can go about this, but for today's presentation, we are going to emphasize the talk mostly on vision and speech-based processing for embedded and IoT devices. So let's take a quick primer on what is always on. So as you can imagine by the definition, always on means it's literally always on, right? Lightweight algorithms that are constantly running on the device, executing all the time, and they're typically served as precursors to more computationally heavy algorithms that would come. So a lot of customers use different names for this: low power mode, standby mode, mode 0, AON, whatever it is, but the usage is still the same. So typical applications that you can see in these type of usages is, device unlock, things like video doorbell, some lightweight gesture control, and you can accomplish this using a number of modalities, right? You've got face detection, gesture recognition, visual wake word, audio wake words, fingerprint, all different sorts of modalities. Now that we've established high level what is always on, let's go into a little bit more detail and understand what exactly are the requirements over here. So, basic functionality that you can expect for this type of a usage is, continuously running or executing on the device. You take input from various different sensors, cameras, microphones, or other, sensors for real-time processing. You're not targeting something to run at 1,000 FPS, probably 5, 10, 15 FPS. System should be able to run maybe traditional algorithms or maybe some AI and ultra low power or ultra low energy. This is key. One place or one number that you constantly see is this less than 1 milliwatt type of a number. So this has given the rise to what we call these light networks for always on usages. And these are meant to run on microcontroller type of devices so that they consume very low power. For example, everyone's aware of these TFLM or the TensorFlow Lite for micro type of networks. But a common problem in this always on domain is there's a limited availability in the public domain. You can't typically go to GitHub and just pick up a network and run it and expect to have a ridiculous amount of energy or power savings. There just aren't too many networks out there. You can probably count that there might be 5 or 10 networks between the examples given from Google on GitHub or the TFLM networks by themselves. So there sometimes need to be some expectation leveling or baseline correction that needs to be done. And what I mean by this is let's take a look at this example. If you look at some of the common examples, you take these from the Model Zoo, GitHub, or wherever, face detection network, for inferencing, typically, one inference, you're looking at about 30 gigamax per inference. Speech voice networks might be 200 megamax, and then, gesture networks may be 10 gigamax equivalent. Same type of networks you want to run in the always-on domain, a lot smaller, right? A person detect network, maybe about 7 megamax per inference. Your audio networks are, in the kilomax, and then gesture networks are also very much smaller. The ratio is several hundreds of thousands in many cases. And to visually illustrate this point, let's take a look at this. This is a ResNet 50. I'm sure everyone is aware of this and heard of this one. Classic classification network, 100 layers, works very well, no problem. But the classification network that you would run on an always-on domain would be something like this, just 12 layers. And this is the one that is used in the TinyML 0.5 or 0.7 benchmark suite to do the basic image classification. So you can see there's a really big difference in what networks you would run on one domain versus the other. So now let's get into, how do you actually use these networks or where do they get applied? So typically, if you're talking about always on, you're dealing with waking up a device. So there are typically 3 stages in how you want to wake up the device. First stage is the detection, where you typically want to ask, hey, is there something over here? The next one is localize and authenticate, which is more about, what is that or where is that thing located? And then once everything is done, you wake up your device, you unlock, you go, you play your games or, social media, all that stuff, the computer is just, all available to you. So if we dive a little bit deeper into this, and we focus mainly on this detection stages where your always on is probably going to be most important, you can see you end up using things like ultrasonic sensors, microphones, fingerprint scanners. The compute requirements are usually quite small over here, less than 250 GOPS. You're trying to use it on some type of an MCU or a low power DSP, doing things like keyword spotting, some light human presence, face detection, and your OS is probably going to be something bare metal or TFLM type of equivalent. But if you go on the higher end side, you can increase your number of GOPS, you can add DSP engines, AI engines, GPUs, NPUs, everything in the world. But you won't be able to satisfy your always-on requirement of ultra-low power. And if we dig this deeper even more, you can have sort of like a good, better, best within this detection stage as well. And there's a lot to cover over here, but if you focus primarily on the typical applications, you can see at the entry level, it's mostly things like proximity detection. In the mid-range, you're starting to do things like keyword spotting, human presence detection. And in the premium system, is doing the same applications, but you're typically doing a lot of IP repurpose. You want to use one modality to do multiple types of processing. So from what we are seeing right now in this mid-range, there's a lot of activity going on over here. Customers have shipped a lot of products with this type of a usage. But now in this premium area, you're seeing a lot of emerging market. People are starting to say, okay, I've got an IP, I want to still use that IP, but I want to do both audio, as well as vision processing. So this comes back to a consideration from an architectural design. How do we go actually about designing the system? And we're seeing multiple different approaches that people are taking in the industry. One is you have an always-on subsystem, which is focused on the detection stage, but you have separate data paths. You have one IP that does vision processing, one that does audio processing, or where the trend is moving now to is saying, okay, I just want to have one always-on processor, but I want to take in vision, radar, LiDAR, speech, all these type of processing, and have one IP that is capable of handling all these things very efficiently and also with good performance. So obviously I've covered a lot of things over here, so let's just go over that for a quick second. So obviously there's a need for always-on, as we've pointed out. A lot of talks at Embedded Vision itself that are highlighting always-on and its importance. Area efficiency with low power consumption is key. Many customers don't want to use a DDR block when they're in always-on. Typically want it to be on chip or maybe even on the IP itself. There's a trend moving to either having discrete IPs to take this processing of various modalities, or you have one IP that does it, capable of processing inputs from cameras, microphones, different types of sensors. And this usually requires to do a combination of CV, AI, speech, FFT, sound detection, and different types of things that I can't even think about right now. A lot of requirements, but fortunately, Tensilica, we have an answer for you. And while we get into that answer, one thing we need to consider is the selection based on dominant processing. And what I mean by that is if you look at the top, you've got various different sensors coming in. You've got different applications that you want to do. But if you draw a line in between, you can see that both of these usages rely on vision as well as speech processing. But the left-hand side is more audio or speech dominant and saying like, yeah, I want to do a little bit of vision processing. Or you can go the other way saying like, yes, I want to do both processing, but I'm going to be more vision focused, and maybe I'll do a little bit of audio processing. We have an answer for both. And if you're more on the left-hand side, we have our Tensilica Hi-Fi DSP family. And on the right-hand side, we have our Vision DSP family, which I will dive into a little bit more today. So the Vision P1, it's our best-in-class low-energy DSP for vision and AI. It's a very scalable solution. It's built on a successful Vision family of products. So we've got our Vision P6, Q7, Q8. We learned a lot from the development of those products, and we came up with a very reduced form of a product that allowed us to come up with the Vision P1. It's a very efficient design. It's 1/3 the size of our already very small Vision P6 DSP, so great for always-on type of applications. Fast time to market because we have all our existing vision and AI libraries that were available on our existing products have been ported also to the Vision P1, so you're ready to go right now. It's a scalable, configurable, and extensible architecture, so all the goodies that you had from our Vision family of products are all available. You can configure the number of Macs. Obviously, you can't change the SIMD width, but you can add options, change instructions, add custom instructions. Everything is available for you. And it also enables compelling use cases. So things like the always-on things, which everyone is interested in, face detection, foveated rendering, proximity detection, and also keyword spotting, because it's a vision processor, but can also do audio processing. So let's go through one of the use cases typically that is considered for always-on, which is human presence detection. So I'm sure everyone has seen this usage where you've got a camera feeding in an image to a CPU, do your device unlock. Nothing wrong with it, works great. But as everyone knows, CPU is probably not the best or the most optimal solution for running CV and AI workloads. This then allowed a lot of customers to introduce adding a DSP or an NPU in the path. And there are a lot of customers who have enabled this type of a solution, where now you have your camera sending your image directly to your DSP or your NPU. It does all your face detection processing, human presence detection, and once it does the detection authentication, tells up the big brother CPU to wake up and unlocks the device. This is good. Many customers have released a solution that uses this type of an approach, but you can still improve the energy profile and power because you're still using the DSP to run a lot of very light workloads and it's on a lot of times. So this is where the Vision P1 actually comes in. So take a look at this example. You have the camera feeding into the P1, but now you're sending a low resolution image in there. You're talking about ISP bypass, a mono or a Bayer image, with just very, very low energy or low power from the image sensor feeding directly into the Vision P1. P1 does the always-on type of processing. Is there a face? If there is a face, okay, I'll wake up my larger DSP or an NPU and send a much more higher resolution image in there. Then I can do my next level of processing, detection, authentication, wake up the device, and you have your device unlocked. So this solution we see as the best, and we see now newer customers implementing this type of an approach because the P1 is designed to run this type of flow where it is on all the time, running in a very low power and energy envelope, and it wakes up the DSP or the CPU subsequently only when needed. Last but not least, also a lot of this always-on face detection is tied to some type of device authentication. So the question always comes up about security. How does secure mode and everything work over here? Well, luckily, you can have your camera memory mapped into a secure zone. Our P1 and our higher-end DSPs are also fully capable of doing secure boot, and you can wrap everything up in a secure mode boundary. So effectively, you can reduce or prevent hijacking and hacking from entities outside. So this could be a really good solution that meets also security requirements in addition to the power and energy requirements of an always-on solution. So one place I wanted to spend a few minutes on was, we've shown all the stuff about, all the different types of usages, but one question comes up is, how does this work against real-world benchmarks? So one question we get all the time is, this TinyML benchmark list is out there. How does it work on the Vision P1? So we ran all the 4 networks that are available on the TinyML suite. There are 2 image networks. So the visual wake word is a person detect, image classification, keyword spotting, and anomaly detection. Ran them on the P1, compared them to public domain data, and in many cases you can see that the performance is actually significantly better than a lot of the publicly provided information that is out there. Aside from performance, and over here also this is not just taking the raw data that was provided on TFL on the TinyML consortium, we actually normalized it for a common frequency and ran it so it became more of an apples to apples comparison. We also compared the energy, and you can see, for a lot of these networks, the difference is actually quite outstanding. It's like several hundred X in many cases compared to running these versus what is on the public domain, which is mostly a lot of CPU-based approaches. So obviously the thing to take away from this is, the Vision P1, though it says vision in the name, it can still do vision and audio processing, specifically more targeted for always-on type of usages. It's an energy efficient and very customizable solution that you can use for various different applications. And it is a sub 1 milliwatt solution for always on with vision and audio. In fact, in many cases, it is a single-digit microwatt solution as well. So it's a very efficient solution that can meet a lot of customers' requirements for always on. I spent a lot of time talking about always on, but I'll just wrap this up by saying that the Vision P1 DSP, since it's part of our Vision family of products, it is also a very efficient Vision DSP. So some places where we're seeing customers do new designs is a smart image sensor, where the idea is you have a pixel array with a stacked die approach, and you have the Vision DSP sitting on the image sensor itself. So you capture and you send out normal images from your image array, but you can also do some smart image sensor processing on there. So region of interest crop, metadata processing. So you load the network directly on the P1 on the image sensor, and you can do all this type of processing directly on the sensor and just send out metadata and reduce the bus traffic. Aside from that, foveated rendering in the AR, VR, or metaverse usage is also becoming quite common, where the P1 is used inside the headset or in the glasses to look at where the eyes are looking. From there, understand pupil direction and gaze direction, feed that into your GPU pipeline, and you get foveated rendering. So we're not replacing the GPU, although we're feeding data into the GPU to assist it to do much better quality foveated rendering. Last but not least, the Vision P1, it is available now. It's not a pre-release announcement. It has been available for some time. All the imaging software tools, libraries, Vision DSPs, imaging libraries, SDKs, support for taking in frozen neural networks, compiling them, running them on our DSPs, TFLM, Android NN, NN API, all the different acronyms you can throw on there. It's all available. The product is ready for evaluation. Out of the box, we can run over 100 networks on there, compiled, optimized, and targeted for Vision DSP or the Vision P1 or the other family of Tensilica products. Last but not least, Cadence booth is right over there. We have a lot of demos. In fact, this Vision P1 always on demo, which does the visual wake word as well as keyword spotting. We have a live demo running out there, so if you want to come and see that, please swing by. We also have other vision and AI demos, and if you have any further questions, you can reach me over there, or my colleagues can definitely answer them for you. So for now, thank you for your time, and open to any questions.
Thank you very much, Amol. Any questions? I have one, at least. I have many, actually.
Sure, go ahead.
I'll come up here. So one question is, obviously, Cadence is a Silicon IP licensing company for as well as EDA tools. But I also think when I think of Tensilica, I think of products like the ESP32, right, where someone has taken a Tensilica processor and made it into a
Which
chip.
was the product? Sorry, I didn't hear it.
Oh, Tensilica, the ESP32,
Okay.
right? Kamiya Espressive.
Okay.
So my question is really, are there, for people who are not planning to make their own chip but would love to avail themselves of the power of the P1, do you at this point, do you have any partners at this point who are planning to make off-the-shelf chips that are based on this that are generally programmable? Does that make sense?
Yes, absolutely. So good question. So there are a couple of things over there. One is, if you want to play with Tensilica, we have a full, there are two ways to go. One is, to answer your question is, do we have partners that we can connect somebody to, right? So one example actually is out there. We have a MediaTek board which has our Vision P6 DSP on there.
Oh, cool.
It's an IoT targeted product. So, if you order it, you have access to the libraries and the tools and everything that you can have. It has the Vision P6 in there, which is the bigger brother of the Vision P1, but the ISA is very compatible, so you can have more or less, you'll have better performance, but the availability of SDK tools and libraries is the same. So that can be one way to go from a hardware perspective if you actually want tangible hardware to play with. Another option is, we do know that this limitation is there because building chips and everything is very expensive. It's not something that, a garage startup can do. So what we have is we actually have, cycle accurate simulators and a full development environment that will allow you to, start with just the IP. So you can do it on a Windows or a Linux-based system. You get a whole Eclipse-based environment. Cycle accurate simulation, so that way when you run your algorithms, you can understand hotspots, how the slotting and the pipeline is working. From there, you can go to a System C model, which can give you a more bigger handle on designing a larger SoC and see how the different blocks maybe play with each other and talk to each other. And at that point, maybe we can introduce you to other partners if that's a way to go, or if you raise enough money, you can build your own chip.
And these days, raising enough money seems to be easy. I exaggerate, but
Yeah, I think if you put AI somewhere in your presentation,
then
you probably get about a few
exactly.
million,
So,
hopefully.
any questions? Yes.
How do you compare the P1 with the Q8 DSP? And can you run Q8 in a very low power in an AOC system?
Sure, good question. So the Vision P1 is, you basically address the whole spectrum that we have, because P1 is the low-end product, not low-end in a bad way, but targeted for low-end applications. So it's a 128-bit SIMD and 250 GOPS type of a thing. Q8 is the high-end flagship product of us, a 1024 SIMD, 3 to 4 TOPS. So advantages, the libraries, our AI framework, our vision framework, everything is all the same. So if you're today on P1, you want to go on Q8, it's very easy. If you're on Q8, you want to come to P1, it's very easy as well. You can always run the Q8 in a very low energy or a low power mode, but it's a much bigger machine and a much powerful machine that it's probably not going to be inefficient for your design. A simple analogy you can say is like you can have a Toyota Prius to go buy groceries, or you can buy a $300,000 Ferrari to go buy groceries. You can drive it at 20 miles per hour, but it's probably not the best use of $300,000 to just go from here to there, right? So it's, you can do it, but it's probably not, you're going to be eating up, area a lot on the design, and that's more targeted for like really, ADAS or, SLAM and those type of applications. So it can run, and we don't limit anyone to run however they want to. But well, the number specifics I can talk to you over there. And that is also a very loaded question because there's a lot of variables over there. It depends on what technology node you're running at, what frequency you're running at, what type of workload as well. So we have specific numbers that we can share with you on DIAGs and workloads that we have run. And if you have an NDA, we can obviously talk to you in detail about that. But yeah, it's to that level. There's a lot of choices that you have to make over there. Like a watt, if you choose 1 watt as a power number for something, it can always change depending if you go from a 40 nanometer process to a 5 nanometer process, what frequency you run at, all those things make a difference. I hope that answered your question. Or we can still talk after this presentation.
And I think we have time for one more question. Anyone with a question? I had yet another question.
Sure, go ahead.
Which is, you had mentioned in terms of memory, right? This is targeted at smaller neural networks and obviously low power. Is there an architectural limit to, for example, how big that neural network can be? In terms of either the address space that's capable of being addressed, number of weights, coefficients, that sort of thing?
Not really. I think it's more or less like right now I've seen it to be mostly like quote unquote a class of networks. So like the networks that typically would meet your TensorFlow Lite for micros API list, because TFLM is sort of like taking TF Lite and saying that okay, I'm only going to support about like 50 or 60 of these operators. So you already subsetted the problem down, bounded the problem down a lot smaller. And then, once you limit yourself to that much, you sort of are also confined to what are really the applications I can do with it, right? I can't do very, very precise, you can do maybe like bounding box type of a thing and all that, but now you're starting to get into that space of like, I have a framework that is meant to run in a low power domain, but I'm trying to run it in a much higher domain. So there's no specific numbers that says that it has to be 500 KB or it has to have this much size. But what we are seeing, at least in our customer engagements, is they're trying to make sure that it's small enough that, and in this case right now, it's mostly just looking at the tiny ML type of networks, but you can obviously build your own network. But if you build the tiny ML networks, it's can fit maybe on some type of on-chip memory rather than going to a DDR and fetching it from there, because that becomes very expensive. So, I mean, roughly you probably have to think like maybe a couple of 100K is the max of what they want to try to shoot or what they want to try to do.
Awesome. Okay, well, thank you very much again.
Thank you.